Hi, hello everyone. I am Soumojit Chatterjee, and this is TLE Eliminators. And this is the post-contest discussion of today's Codeforces Round 994, Diff 2. And today we will discuss the first four problems, A, B, C, and D. So let us quickly start and discuss the problems one by one. Okay. So let me start with reading the problem number A. So here it is. Everywhere, the dragon found an array A1 to An of n non-negative integers. In one operation, they can choose a non-empty subarray B of A and replace it with the integer MEX of B. They want to use this operation any number of times to make A only contain zeros. It can be proven that this is always possible under the problem constraint. And the question asks, what is the minimum number of operations needed? And it says that the minimum excluded mix of a collection of integers f1 to fk is defined as the smallest non-negative integer x which does not occur in the collection. Okay, so let me explain the problem statement once. So let's quickly start. So what does the problem statement say? First of all, let us be clear a bit clear with the definition of mix. So basically, mix of a set of numbers. So suppose I have a set of numbers set of numbers. The mix of such a set of numbers is the smallest non-negative integer which is not present in this set. So in this case, this is 0 because 0 is not present in the set, and this is the smallest such number which is not present in the set. Similarly, the mix of a set say 0, 2, 3, and 7 will be simply 1 because 1 is the smallest non-negative integer which is not present in this set. So I hope the definition of mix is clear. Now let us understand what the problem statement actually asks for. So the problem statement says that they will give us an array A1, A2, A3, En. And what can we do in one operation? In one operation, we can choose one segment. So we can choose one segment and then we can convert this entire segment into its max value. So we can pick this segment, we can pick this set of numbers, and we can convert this set of integers to its max value. So suppose its max value is mx. So it gets converted to ms, and then the rest of the part of the array remains same. So basically it happens a1, a2, and then dot dot an. So this is basically a transformation, and this is a single operation. And the question asks for what is the minimum number of operations needed so that the entire array becomes an array of zero. So basically, I have this array A, which is provided to me as input, and I have to do some minimum number of operations so that it actually becomes an array of zero. So this is what the question asks. Okay. So how can we approach the problem? Uh, so this problem was actually a bit difficult side, or we can say that something which is usually a more difficult than what a standard diff2 looks like. But then there are cases to analyze, and then if you realize the cases well, the problem will get solved. So here, this is the first case to think about. The first case, and this is the most trivial case. What if A is simply an array of zeros? So what if array A is simply an array of zeros? In that case, we obviously do not need any operation, right? Because our objective is already satisfied. So in this case, our answer would be simply zero. We do not need any operation to solve. We can also look in the problem statement itself that okay, let's see, whenever the test case is all zeros, the answer is simply zero and nothing else. Okay. Yeah, sure. So this part is clear. Apart from that, there are a few more cases to look up at. So suppose I have a set of all positive integers. This is one case where the entire zero is zeros. The entire array is composed of zeros. Now let us look at the second. Suppose A is an array which contains only positive integers. So there are no zeros. There are no zeros in this array. So if this is the case, that there are no zeros in the array, then you need to realize, then what can we do? We can take this entire set of numbers, right? We can take this entire set of numbers and do an operation on it. So what will happen if we do an operation on this entire set of numbers? What is the mix of this entire set of numbers? It's zero, right? Because zero is not present in this set, and it is the smallest such element not present in this set. So by definition, the set of this number, the mix of the set of these numbers is zero. So in that case, using just one operation, we can convert it to a zero, right? So in this case, when there are no zeros in the array, the answer is simply one. The answer is simply one and nothing else. Now there is a third. What is the third case? The third case is, what if I have a single block of positive integers? So like here this is a block of positive integers, and we realize that we can do it in just one operation. So what if A looks something like this? A is a bunch of zeros, and then a block of positive integers. So 7, 3, 2, 4, 6 again comes, and then again a bunch of zeros and nothing else. So if A is something like this, realize that there is only one block of positive integers, and you can again pick this block of positive integers, do an operation on this, and in one operation you will get all zeros, right? So that means again one operation is sufficient to convert this array to all zeros. So even in this case, the answer is one. So if there is only one single block, there is a single block of positive integers, the answer is one, right? Now what can you do in other cases? So there are three simple cases we analyze. Now look at some other cases. Uh, in some other cases, so there are maybe multiple blocks of positive integers. So suppose you have a bunch of zeros, and then you have a 7, 3, 4, 6, and then you again have a bunch of zeros, and then you again have a set of positive integers and something like that. So realize that you actually have multiple bunch or multiple blocks of positive integers in your. So in this case, obviously one operation does not satisfy, right? One operation does not satisfy. You can never do it with the one operation, because if you pick this segment, then the mix of such numbers is not is zero, but then this segment will remain, right? So what can we do? Note interestingly that all these arrays can actually be done with just two operations. How? The idea is simple. You pick the entire array one. If you pick the entire array one, you will get some value, right? Some value k, which is not zero, right? Because the mix of this bunch of numbers is not zero, there are zeros present here. So you will get some integer k, a single element in the array, which is not zero, right? In just one operation. And if you have a single element present in the array, with one more operation, you can get zero, right? That means just two operations are enough to solve the problem and make it to entirely zero. So what is the solution? Then what is the solution? Let me conclude the solution. The solution is simple. You need to check four cases. The first case is when the entire array is zero. So the entire array is zero, and then we know that the answer is simply zero. The second case is when the entire array is positive. There are no zeros. There are no zeros, and in this case, we know that the answer is simply one. Just one operation in. The third case is only when there are one block of positive integers. So you have 7, 4, 3, 2, and then you have zeros, but then you have nothing else. You have just one block of positive integers, and in that case also we know that the answer is simply one. And the fourth case is when you have multiple blocks of positive integers. So you have a lots of zeros, and then you have numbers which are positive integers, and then again you have a bunch of zeros, and then again positive integers. So in this case, what happens is you have multiple blocks which are non-zeros, and then I have shown that how you can first do an operation on the entire array, and then you get an integer k, and then you do an operation again on this array, and using just two operations you can solve the problem. That means the answer is always 0, 1, or 2. You can also look at the test cases and you will realize that all outputs are either 0, 1, and 2. Here is a code which explains the approach, and the code is actually implemented the way I have told the approach. So first, I take the integer as input, After that, I take the vector as input. Uh, C, this C integer basically denotes the number of zeros in the array. So here it is. We count the number of zeros in the array here. So if C equals n, that means the entire array is composed of zeros only. So in that case, we output 0 because we do not need any operation. Else, if we see that C equals 0, that means the number of zeros in the operation is 0. That means we will need just one operation, right? So this is basically, it hits this case. The case where all integers are positive, right? The case where all integers are positive because there are no zeros. So in that case, we know that the answer is 1, right? So that is what I have done. If C equals 0, so there are no zeros, so the answer is 1. If that is not the case, then here this is a standard technique to count the number of blocks, the number of positive blocks in the array. So I have made a vector where I have basically stored the length of the blocks. The lengths were not required, but I've stored them. So here what I do, the count variable maintains the number of contiguous ones I have seen. So we basically increase the value of count, and whenever we encounter new zero, we push the count in our vector. So basically, after this entire operation, the vector VB stores the number of zeros, stores the number of positive blocks in the array, and then as our logic suggested, if the number of positive blocks in the array is greater than one, then we will need two operations. Otherwise, we can do it in one operation. Okay. So this was the idea for the problem. So I hope it is clear. Great. Now we can move towards the second problem, problem B of the concept. Okay. So this is the second problem. So let me quickly read it. So it says that given a string S equals S1 to Sn of length n consisting of characters P, S, and dot, determine whether a permutation P of length n exists such that for all integers I, uh, if Si is P, then P1 to Pi forms a permutation of length I. If Si is S, then Pi to Pn forms a permutation of length n minus I plus 1. And if Si is dot, then there is no additional restriction. Okay. So this is what the question asks for. Just a second. Great. Uh, okay. So permutation of length n is an array consisting of n distinct integers from 1 to n in arbitrary order. Okay. Uh, so let me first explain the problem set. Okay. So let us quickly move. Okay. So let me explain what does the problem statement ask for. The problem statement says that we will be given a string s as in. So we will be given a string s as in. So that's basically n characters, right? So that is basically n characters, and this is given in the input. And it is also said that an SI can be either a P or a S or a dot, right? These are the three characters which SI can be. And the question says that given this string, so you are given this string S1 to Sn, you basically need to construct a permutation. So basically, you need to construct a permutation P. So you basically need to construct a permutation P such that some conditions hold. So before discussing the conditions, let me clarify that what is a permutation P? A permutation P of length n is simply some reordering of the array 1 to n. So I hope it is clear. So you have the array 1 to n. So any valid reordering of this array is a permutation of length. For example, uh, 5, 2, 1, 4, 3. This is a valid permutation of length 5. So this is a valid permutation of length 5. And 5 to 1. This is not a valid permutation. This is not a valid permutation of length 3. Because of length 3, you should have exactly 1, 2, and 3, and some reordering of this in the array, which is not the case here. So I think what is a permutation is clear. Okay, the question basically asks for that you have a string S1 to Sn, and then you have to print a permutation and you have to print a permutation which satisfies some condition. What is the condition? The question says that suppose you have some character Si which is equal to P. So suppose you have some character Si which equals to P. So here P denotes the prefix. So if Si equals to P, if this is P, then basically this part of the permutation must be a permutation itself of length I. So this part of the permutation must be a permutation itself of length I. And suppose there is some one more character Sj, which is equal to S. So basically the condition is that if Sj is S, then this part of the string should be a permutation of whatever length the remaining suffix is, n minus j plus 1. So this part should also be a permutation of length n minus j plus 1. That means, okay, let us quickly understand this with an example. So let me pick a test case. So let me pick the first test case, s.sp. So if we look at a test case, s.sp. So basically we need to create a permutation of length 4. How do we need to create? Because this is P, this basically ensures that the first 4 characters must be a permutation of length 4. And since this is S, it says that end from this end 4 characters must be a permutation of length. So basically, this P and S enforce the same condition. This S says that the last 2 characters must be a permutation of length 2. And this dot enforces no extra condition. So realize that you can actually have a permutation like this 1, 2, 3, 4, isn't it? So here the last 2 characters form a permutation of length 2 because 1, 2 is a valid permutation of length 2, and the all the 4 characters itself 4, 3, 2, 1 is a valid permutation of length 4, right? So this makes complete sense. So for s.sp the expected answer is yes because there exists a permutation. Uh, so the so the answer is yes. So in the answer we do not need to print the permutation. We just need to print that whether it is possible to solve the problem to find the permutation or not. Also realize that the sum of n overall test cases does not exceed 5,000. That means that means here it is given that n does not exceed 5,000. So basically, they expect. So basically, the authors expect to write an order n square code for this. But interestingly, this problem can actually be solved in order n time. This problem can be actually solved very fast enough, even faster than what the time limits request us to. But and there are small observations which needs to be made to solve the problem. So here there are a quick checks which we can do to solve the problem. So realize this. So think about this. That suppose in the string in some string I have a p here and then I have an s here. Suppose this is a string where I have a p here and an s here. Now what does this p indicate? This P indicates that this part of the permutation must be a permutation in itself, right? So one must be a part of this permutation because all valid permutation must contain one, right? So since this part P indicates prefix, so that means one must be a part of this part of this area. Similarly, S indicates that this part of the segment must also contain one because this is also a valid permutation. But look at this. In this entire permutation, you have a 1 here in the left side of P and you have a 1 here in the right side of P. That means you must have at least 2 ones to satisfy the condition. But that is not possible because we need to print a permutation, right? And a permutation, uh, for it to be valid, there should be exactly 1 1 in the array. But here we have greater than equal to 2. We need greater than equal to 2 once to satisfy all conditions. So that means that this is a contradiction. This is a contradiction. And the answer for all such test cases is definitely no. So that means in a string, whenever a p comes before some s, so the answer is definitely no. You can also look at the test cases to verify this. So look at this. A p comes before s, so the answer is no. Even here, a p comes before s, so look that the answer is no. In most of the cases here, so here a p comes before s and the answer is no. So whenever a p comes before s, the answer needs to be no because there is a contradiction. Because if a p comes before s, then we would need at least two ones to satisfy all the conditions, which is not possible in a permutation. So I hope that is clear. Okay. Now here comes the second test. Here comes the second test case that the string contains only p. Suppose there is a string which contains only p. So basically no s. Now what does this p enforce? Like this p enforces that this part of the string must be a permutation, right? And this p enforces that this part of the string must be permutation. This p enforces that this part of the string is an input, is a permutation. Now realize that if there is no s in the string, I can always create a permutation like this: 1, 2, 3 dot 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 in, right? So whenever you have a p here, so this part is obviously a valid permutation. So that means if you have a string p, if you have a string which is purely consisted of p and dots, no s, then you can always give the answer as yes, because you can always have a valid permutation 1 to n, right? Okay, so this is the second test case. Similarly comes very similarly comes the third test case when you have only s. So this is a string where you have only s and there are no p's. Now realize that if there are no p's, then what does this s conditions enforce? So exactly very similarly, so s indicates that this is the prefix, this s indicates that this is the prefix, and this s indicates that this is the prefix. So that means we can always create, in this case, a permutation of this format, right? N minus 1, n minus 2, and dot 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 1, right? So here, any suffix you pick, that would be valid permutation. So in that case, that means that if there are no p's, then also my answer is yes, because I can always have a valid permutation, right? So this problem is also solved. Okay, so here comes the third. So we have filtered out some no conditions where a p comes before s. We have also filtered out conditions where the strings are completely composed of p's and s. So here comes the third case. Look into it. Suppose I have some s, and then I have again some s, and then I have p, and then I have again some. Suppose this is the configuration of this. Okay, so realize that there is a problem, which will occur. Why is there a problem? First of all, due to this p, this part of the string must be permutation, right? So if this part of the string is a permutation, then consider n. Since this is a permutation of size less than n, that means n must be here. N must be somewhere here, right? N cannot be here, because if n is before this p, then this part of the string cannot be a valid permutation. Similarly, what does this s enforce? This s enforce that this part of the string is a valid permutation. But if this part of the string is a valid permutation, that means n has to be this side, right? N cannot come inside this. But wait, this is again a similar contradiction. You have two n's in the array. One says that the n has to be in this direction, and one says that the n has to be in this direction. That means that such a configuration also will lead to a contradiction, and therefore the answer will be definitely no. So the answer will be definitely no. Because whenever you get such a string, in order to satisfy all conditions, you will need at least two n's. One in this direction and one in this direction, which is not possible to have in a permutation. Okay. So if you combine these cases and try to play with these test cases in pen and paper, you will realize that the final solution looks something like this. So here is the final solution. The final solution is very clear, that we know that we can't have 2s and 2p at the same time. If we have 2s and 2p at the same time, then it will definitely be a contradiction. Similarly, we so basically, in order to be a valid answer, so all valid answers. So if I try to list what are valid answers, or basically answers uh, which give yes, so there are only few cases for types of valid answers. So the first type is a pure string of p. We have already discussed this, why this is valid. The second is a pure string of s. We have also discussed why this is valid. The third case, which is a valid, is that you have one s and then you have remaining all p. Note that this is a valid case because you can always have a permutation like 1, 2, dot dot n to satisfy all the p conditions, and the s condition necessarily gets satisfied because 1 to n is itself a valid permutation. So you have exactly one s. So you have exactly one s, and the rest of the string is completely comprised of p. So in this case also we return yes. And there is one more, and that is you have lots of s. Okay, so you have lots of s. So you have lots of. Okay, just let me erase this. So basically, you have lots of s, and then you have finally a p. So even this is also valid. Because of the same reason that you can have a permutation like n minus 1 n minus 2 dot 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 1 here in this. Apart from this, in all other cases, my answer is no. Why is my answer no in all other cases? Because very simply, if you have 2s and 2p, then you will get a contradiction as I said like this. And if a p and if you have a p which comes before it, then also it is an issue because then we get a contradiction like. So I hope the idea is clear. Let us quickly go through the code. Uh, so here is the code for the problem. Okay. So here it is. First of all, I've taken the input as n. I have taken the string as the input. Here I've marked two integers, ss and pp. Ss basically indicates the frequency of s in the string, and pp indicates the frequency of p in this. You can look in the code that whenever I encounter s character in the string, I increase the value of ss, and whenever I encounter a p character in the string, I increase the value of p. Okay. And then if either of SS or PP is 0, then that basically hits the pure string case. And in that case, we can actually print yes. Apart from that, I also mark two integers SI and PI. SI stores the last ending most index of the string, and where S is found, and PI indicates the first character of the string where P is found. Now simply if SI is 0, that means S comes before, or PI is n minus 1, that means P comes after, we return yes, otherwise we return no. So basically this checks the last two conditions, right? Like if S, like here, what we realize that is that if S comes before, so this is the SI equal to 0 case, that S comes before, or if this is the case, like P comes after, so here PI equals n minus 1 case. So P comes after. So in these cases we can make. So we actually do print a yes in all these cases and no in others. So that is what the code implements. The idea is very clean and can be implemented easily. Okay, so I hope I'm able to make this clear. So now let us start discussing problem C of the contest. Okay, so let me read the problem statement first. So the problem statement says that you are given integers n, x, and y. There are n dragons sitting in a circle. The dragons are numbered 1 to n. For each I from 1 to n, dragon I is friends with dragon I minus 1 and I plus 1, where dragon 0 is defined to be dragon n and dragon n plus 1 is defined to be dragon 1. Additionally, dragons x and y are friends with each other. If they are already friends, this changes nothing. Note that all friends are mutual. What do we need to output? Output n non-negative integers a1 to an, such that for each dragon I, the following holds. Let F1 to Fk be the friends of dragon I, then AI is simply mix of A F1 to F. Okay. So let me quickly explain the problem set. Okay. So here is the problem statement. The problem statement says that it will give first an integer n. What does n signify? N is simply basically, uh, uh, it basically says that there is a cycle of length n. So here comes the cycle of length. The question says that there are n dragons sitting, which you can think of actually as a circle. And the question says that any dragon in this circle. So look at dragon number 3. He's friends with dragon number 4 and 2. So it is like a bunch of people are sitting in a circle, and every person is in friend with the people who are sitting adjacent with them. Okay, so the setup is clear. Apart from that, the problem statement says that it also gives us input two integers x and y. Okay, so what to do with x and y? It says, note that x and y will appear somewhere in the array. So it says that x is also friend with y. So that means apart from this original cycle, there is also one extra edge or one extra friendship between x and y. Okay. So all clear. So what does the question ask? So let me draw the diagram once again. So we have some cycle, one, two, three, and it goes. So we have some cycle, and here we have n. And then there are two nodes which are also marked. So here there is x and there is a y. So there is a friendship between x and y, which is also said. The question says that print an array. So basically, for every integer, we need to assign an element: a1, a2, a3, a4, something like an. So basically, every integer, we need to assign an element such that what happens? It happens that for every node, if you look at his friend, then the mix of the values of his friend is simply his own value. That means if you look at 2, then what is the mix of his value of his friends? That is simply mix of a1 and a3, right? So that must be a2. So this is the condition for node number 2. Similarly, there are conditions for all nodes, and we need to print such a value of the array such that all of these conditions hold simultaneously. Okay. So I think the problem statement is clear. So great. So we can discuss the solution one by one. So first of all, let us throw away this xy. Let us throw away this xy edge and try solving the problem when there is no xy edge. Or say that the xy edge is again adjacent, so that does not increase any information about the friend. First of all, let us solve about this simple case, and then we will try to extend the solution to the case when the xy edge is present. So, suppose the xy edge is not present, and suppose n is 5, n is 6. So, let us look at this case: 1, 2, 3, 4, 5, and 6. So, here we have a cycle. We need to assign an integer to every cycle such that the mix of its value, such that its value is basically the mix of its neighbors, right? So, on quickly with some observations, you will realize that one great easy labeling which also works is simply the 0 1 0 1 0 1. You just repeat every node with an alternate color. Look at n equals 6 uh, and note that such a labeling is actually valid because any zero node sees all his neighbors as one node and the max of one is zero itself. So this condition works. Similarly, every one node sees all the nodes as zero itself, and the max of all zeros is one, right? So this condition also works. So that means for an even length cycle, we can just color it as alternately zero and one, and the labeling holds. This happens for any even length cycle. Consider n equals 4. So you have a cycle like this. So you can again color mark them as 0 1 0, 1. And this is a valid color. Great. Okay. So now let us also try to solve the problem for odd length cycle. So here it is. So suppose we solve the problem for odd length cycle. So suppose n is 5. So here it is. So 1, and then comes 2, and then comes 3, and a 4, and a 5. So here it comes. So how will you color this? So why not extend the idea of even cycles to odd cycles also? So I mark this as 0, I mark this as 1, I mark this as 0, I mark this as 1. But now look at this. I can't mark a 0 here, right? Because what does this node see as its neighbor? As its neighbors, this node sees 0 and 1, right? And what is the max of 0, 1? What is the max of 0, 1? The max of 0, 1 is 2, right? The max of 0, 1 is 2. So we actually need to assign this value as 2. But note that if I assign this as 2, then also all other nodes values remain valid. Like look at this 0. This 0 sees 1 and 2 as its neighbors. And the max of 1 and 2 is 0, right? So this condition holds. Similarly, look at this 1. This 1 sees 0 and 2 as its neighbors. So so the max of 0 and 2 is 1. So even this condition is valid. That means that for any odd length array, what we can actually do is we can mark some one node as 2, and then we can rest for all other nodes. We can simply alternate the labeling between zeros and. So that is the idea. So even for say n equals 3, a simple triangle, the idea is simple. So here is a triangle. The idea is simple. You mark one node as 2, and for the rest of the nodes you can just label. So for any odd length cycle, you can just mark one node as 2, and then you keep on labeling the rest of the nodes alternately as 0. So I hope that this idea works. Now, how will we extend this idea to the problem when there is an edge between x and y? Think about it. So the problem now is something different. The problem here is that I have a cycle. So let us play with cycles of length, say n equals 6. And now I have an edge between. So suppose this is x and this is y. For pure cycles, we knew how to solve the problem, right? But how to solve the problem for these cases when there is an edge x and y between? So you realize that when you add an edge between x and y, you basically break the original cycle into two different cycles. And these two different cycles are pure small cycles. And we can actually use our previous idea to find the solution for these two cycles and then merge. Exactly what is the idea? You basically mark x as 0 and you mark y as 1. This we can always do, right? Now, if I mark x as 0 and y as 1, now look at this cycle. This cycle is a 1, 2, 3, 4 length cycle, right? So if this is a 4 length cycle, we know for even length cycles, the simple solution is toggling and alternating zeros and ones. So if this is 0, we can simply mark this as 1 and we can mark this as 0, right? Similarly, this is also even length cycle. So we can keep on just toggling. So if this is 0 and this is 1, then we can just mark 1 and 0, right? So simply, a solution which we actually designed for pure cycles also very easily extends to the case when there is an edge between x and y. So think about this. Let us also play with few other test cases. So suppose this is a test case. Okay. Suppose this is a test case. Let me erase this. Okay. Great. Uh, so now suppose there is an edge between x and y. Think about it like this. How will you solve the problem? Simply mark x as 0, y as 1, Look at how the cycles are formed. This cycle is an even length cycle. You can simply alternate between 1 and 0. This cycle has 1, 2, 3, 4, and 5 nodes. That means you have to do something with this. So you have marked this as 0, you have marked this as 1. Keep on marking this as 0, this is 1. But here, because this is an odd length cycle, we cannot mark it as 0 again. These two will be same. We need to mark it as separately as 2. That was our idea with odd length cycles, right? That mark one of the nodes as 2 and keep rest of them alternate. So this is basically the idea for the problem. Any problem can actually be solved very similarly. So, so for any problem, say we take a pentagon, and then we have this loop x and y. So the first idea is mark x as 0, mark y as 1. Look at the cycle separately. So this is the triangle. So this is 0 and this is 1. So we know this is the odd length cycle. We need at least 1, 2 here. And look at this. This is a 1, 2, 3, 4 length cycle. So we can just keep on alternating our idea. So this was basically the idea for solving problem number C. That you first solve the problem for pure cycles, and then extend the idea to the case where there is actually x and y, and that would actually help to solve the problem. And you would also realize that the output to the problem statement was actually hint to this problem. Like all the cycles were actually colored using 0, 1, and 2 simply. So that gave me a hint that okay, most probably only the integers 0, 1, and 2 would be sufficient to color all cycles, probably. And that actually worked. Okay. So here is the code for the problem. We can have a look at it. The code implements the same idea I just discussed now. So here is the code. Okay. So we first pick n, x, and y as input. Then we handle the case when say x is 1 and y is n. So when x is 1 and y is n, then there is already an edge between x and y, right? So so basically this is just the case when we are solving for pure cycle. So for solving for a pure solid cycle case, we break it into two cases when n is even and when is odd. When n is even, we know that we can simple alternate between 0 and 1. So I've done that using I modulo 2, which basically alternates between 0 and 1 as I increases. Apart from that, if n is an odd length cycle, so I have colored n minus 1 nodes, similarly alternatingly 0, 1 and 0 and 1 fashion. And then finally the end node I have marked as 2, which that was our logic, right? For odd length cycles, we basically mark one node 2, and for the rest of the nodes, we just keep it alternating, right? So this was our logic for x equal to 1 and y equal to n, because this is the case where basically x and y does not add any extra edge, right? Similarly, y equals x plus 1, that means y and x are already consecutive. So adding an extra edge between x and y does not make sense. It is already present. So we do the same thing here. This is basically a pure cycle for n even and n odd. I have just copied the code from here and here, and it does the exactly same thing which we discussed. Apart from that, this is the part of the code which I have written for the case where x and y are separate. They are like x and y adds an extra edge and breaks the original cycle into two cycles. So here I take the same idea. I have used this minus one to basically switch from one based indexing to zero based indexing. Okay, so I use the same idea. Vx minus 1 is 0, Vy minus 1 is 1. So that means basically we mark the x node with color 0 and the yth node with color 1. Then I move from the x node to the yth node, simply alternating. Like I mark Vi as 1 minus Vi minus 1. So if Vi minus 1 is 0, then I mark Vi as 1. And if Vi minus 1 is 1, then we mark Vi as 0. So that means I just keep on alternating between the path from x to y. So the idea is something very simple. The idea is like this, that I basically have a cycle 1, 2, 3, and then a dot dot, and then have some x here, and then it goes again, and then I have some y here, and then it goes again, then I have n here, and then this. So basically, From this, the loop first traverses from x to y plus x to y and marks them in an alternate fashion. So that is what I have done. Okay, just a second. Okay, so I was facing some problems. Sorry for the issue. But the idea is, same. So I go from x to y. You just keep on alternating the value. That is what the code does. So it moves from x to y and just alternating the value, assigning a value different from the previous one. And apart from that, if it reaches y and it sees that two values have become equal, then it marks one of them as true, right? That was the logic for the odd arrays. That if you see that while marking alternating, that two values have become equal, then you just assign one of them as true. I do the same thing for the different case. I basically now go from y to x in the reverse direction, and I count the length of the cycle. And if the cycle is odd length, then I mark one of the node after y as 2, and then I keep on alternating between the other nodes. And if count is even, that means I do not need to mark any node as 2, and I just move and count as I mark everyone as alternate, and then I print the vector. So basically, the code may look a bit messy, but basically the idea is very simple. The idea uses just the fact that if you have an even length cycle, you can just or mark them alternately 0 and 1 to satisfy all the conditions. And if you have an odd length cycle, then you have to mark one node as 2 and the mark all the other nodes alternating in 0 and 1, and then it will satisfy all the conditions. And then if you can add an edge xy, uh, just a second. Yep. So if you add an edge xy, then that same idea extends really well. Okay. So I think we are clear with problem C. So we can start discussing problem D now. So let me read the problem D problem statement first. So here is what it is said, that you are given a grid with n rows and m columns of non-negative integers and an integer k. Let I comma j denote the cell in the ith row from the top and the jth column from the left. For every cell I comma j, the integer aij is written on the cell I comma j. You are initially at 1 comma 1 and want to go to n comma m. You may only move down or right. That is, if you are at I comma j, you can only move to I plus 1 comma j or I comma j plus 1 if the corresponding cell exists. Okay. Before you begin moving, you may do the following operation any number of times. Great. What is the operation? Choose an integer I between 1 and n and cyclically shift row I to the left by 1. So formally, simultaneously set aij to aij mod n plus 1 for all integers. Okay. Note that you do not do any operation after you start moving. After moving from 1 comma 1 to n comma m, let x be the number of operations you have performed before moving, and let y be the sum of integers written on visited cells, including 1 comma 1 and n comma m. Then the total cost is defined as kx plus 1. The question asks to find the minimum cost to move from 1 comma 1 to n comma m. Okay, so let me explain the problem statement. Okay, so the question says that it first gives us input two integers n and m, and then it basically gives us as input a grid. So basically, it gives an input a, a grid of size n into m. There are n rows and there are m columns. And just like the standard convention, uh, so they call the I the ith row and the j columns intersection as I comma j, and the value which is stored in aij in I comma j is ai. So this is the standard convention which the problem follows. Okay, and now the question says that you have to actually move that you were initially at this position 1 comma 1, and now you have to finally move at this position n comma m, and you have to do in such a way that it minimizes some cost metric. We will discuss the cost metric, but before that, note one thing about the operation. The problem statement says, okay, so the problem statement says that uh, if you are here at 1 comma 1, and suppose you need to reach n comma m, the problem statement says that the only moves you can go are down and right. So you can only go down and right and nothing. So here is the direction you can move to. That is the problem statement says, and in this way, we have to find the minimum cost, to travel from 1 comma 1 to n comma n. Now, what is the cost? The problem says, okay, before that, the problem gives power to do an operation. What is the operation? The problem says that suppose this is the grid. So let me draw this. Suppose this is the grid, and then this is some row of the grid. This is some row of the grid which contains the values 8, 12, 10, and 25. This is just for an example perspective. Suppose this is some row of the grid which contains this value. Then you can do one operation. You can do one operation on this as per the problem statement. And the problem statement is basically, if you do one operation on this row, then you select a random row. You can also select this row, and then you do a cyclic shift on this row. What does a cyclic left mean? That means basically all elements will go to their left. So basically, a cyclic left shift will convert this array into this form. It's 12, 10, 25, 8, right? So this is what we call a cyclic left shift. And the problem statement says that the operation of this, that the cost of this operation is, so if you want to have one cyclic left shift, then you basically need to provide a cost of k. Okay. Now let us analyze what is the cost of the path. So basically, so basically, the problem says that you are given a grid. So the problem says that you are given a grid. You have multiple rows in it. You have multiple rows in it, and suppose you do x number of operations. Suppose in one operation you can do cyclic shift on any one of them, in any one of the rows. So suppose in one operation you pick a row and then you do a cyclic shift, and then you do x such operation. Then the cost of just shifting stuff is kx, right? The cost of shifting such stuff is k. And the problem says that the path to move from 0 comma 0 to n minus 1 comma n minus 1, the cost for the path to move is simply the sum of the values you get in the path. So here are the sum of the values you get in the path, and the cost to the path is simply that. So if that is the case, let me call this sum of the value as y. So basically the total cost is kx plus y. That means we need to very smartly choose which of the rows do we need to do a cyclic left shift, so that this sum of the values actually reduce. Okay, let me quickly show you this through a test example so that you will understand clearly. Basically, let us take this example 34952401111. So this is, so let me take this test case. So this is 349, and let me look at the problem now. Just a second. Okay, so this is 34952401111. So this is 349, and then we have 524, and then we have 0, 101, and 101. So suppose first forget about the cyclic left shift. So if I do not make a cyclic left shift, then what is the cost to move from 1 comma 1 to n comma n? That is simply taking a path with the minimum sum, right? So this is the minimum sum. So if this is the minimum sum, then what is the cost? The cost is simply 3 plus 4 plus 2 plus 4 plus 101, right? So what is this? 3 plus 4 is 7, 9, 13 and 101. That's 114 cost, right? So the cost is 114 if you do not actually make a cyclic shift. So what should I do? Let's try making a cyclic shift. The value of k given in this problem is 100. So it is given that the cost of one cyclic shift is 100. So why not? Why not cyclic shift the last array? Realize that if I make one operation with a cost of 100, then this is what my array becomes: 349, 524, 101, 101, 0, right? So this is actually a great situation. You paid a cost of 100, but now you get this cheap path. And the cost of this cheap path is 3 plus 4 plus 2 plus 4, which is 13. So that means the total cost. That means the total cost is 100 plus 13, right? This 100 plus 13. So the total cost is 113, which actually beats the cost when we do not make any cyclic left shift. So that means cyclic left shifts are necessary because that will help to reduce the score, right? So there is some way we need to handle. Now there is one important thing to note in the problem, which is a very clear hint of how to solve the problem, and that is the values of n and m. The value of n and m is given 200. So if the value of n and m is given 200, what does that mean? So it is given n is 200, m is 200. So that means that the problem setter actually asks for an O of n cube code. If I just assume for the time being that m equals n, so the problem setter asks for an O of n cube code, because an O of n cube code will take 200 cube, which is approximately 86 times, which is significantly less than 1/8, and it will probably pass all the time constraints. Uh, so basically, the objective is to design an big O of n cube algorithm. Now let me quickly tell you the idea. So the idea is, why not in these grid problems when we are trying to find the minimum work, the minimum cost, then usually what we do is, just a second. Okay. So yeah, in these grid problems, whenever we are trying to find the minimum cost, an usual idea is to compute DP, is to use a dynamic programming tip. So let me compute DPij, and why not also store the number of cyclic left shifts we make at the ith. So dpi comma j ijs is nothing but the minimum cost. The minimum cost to move from 1 comma 1 to I comma j, such that such that cyclic left shift, such that such that the ith row such that the ith row is ith row is cyclic left shifted s times, right? So is cyclic left shifted s times. So this is basically the idea of the problem, that we maintain dpij, where ijs represents that suppose if I have this grid, and this is the cell I comma j. So what is the minimum cost to go from 0 comma 0 to I comma j, such that this ith row has been left shifted s times. So that is what our dynamic programming state represents. So now let us see how can we write the transitions for this problem. So note that if I need to move, if actually need to come and reach this I comma j, I can go in only two directions. Either I go sidewise, or I go down, right? So that means basically there are only two paths. So basically when I am writing dpijs, that should be the minimum of two paths. The minimum of two is, the first move is simply when you move left. and the second move is when you move down. So these are the moves which we can take. Now look at what happens. Okay, now let me draw this, and suppose this is the ith row, and we are trying to fill this cell dpij. So note that the the so we have to move from this cell in the right direction from I minus 1 comma j, right? And since we have sorry, this is the I comma j minus 1 cell. So we have to move from I comma j minus 1 to the right direction in order to reach I comma j. And since we have already moved we have already moved to the ith row. So basically, this should be a transition to this should be a transition to dpi j minus 1 s, right? So basically, dpi j minus 1 s is basically the cost to reach this cell of the array, and then uh, we just need to move rightward, and that would add a cost of this value, right? Because the cost is the sum, so this would add the cost of a I. But what is the value j here after s shift? After s shift, the value which was at already at j plus s would have come here, right? So that plus a I j plus s modulo m. So this is the transition. So this is the transition we take. Also, now look at this down operation. When you are doing a down operation, the transition is not that simple. Why? Because if you look at this grid, if you look at this grid, so here is the ith row. And in our dynamic programming state, we are trying to remember how many shifts we have made at the ith. But think about the I minus 1 row. We just don't know how many shifts we have made to the I minus 1 row, right? So we are moving downward from the I minus 1 row to the ith row, but we do not know how many shifts s dash we make in the I minus 1 row. So this is actually tough. Uh, so that means this time of the transition, we just must have dp I minus 1 j s dash, right? And then we have to take over all s dash, minimum over all s dash from 0 to m minus 1, right? Because we do not know how many shifts we have made in the penultimate while calculating dpij, right? So we have to iterate over all possible shifts we have made in the I minus 1 row and calculate. But now since we are in the I minus 1 row and we are entering the ith row needs to be shifted s times, right? So here there is an extra cost k. And this has to be done because when we are going from down to from the I minus 1 row to the ith row, we are basically inserting inside a new row. And when we are entering inside a new row, we also need to add the cost of shifting, right? So that this is dp I minus 1 j s dash plus ks plus this term. This term would be definitely common in both of them because you are at the end of the day entering the I comma j cell, right? So this term a I j plus s modulo. So these are the transitions. So these are the transitions we have written, which probably works. Uh, so now think about it. Okay. Now think about this. So here there is a problem. Why is there a problem? Because let us look what is the time complexity of the solution. So let us think about this. What is the number of DP states? So what is the number of DP states we need? So the number of DP states is basically n for the ith coordinate, and then we have j. For j we have m, and then we have also have s, right? For this we have an extra m s again, because there can be m number of shifts. The number of shifts can be anything from 0 to m minus 1, right? Making more than m minus 1 shift will not matter because making 0 shifts and m shift keeps the and making m cyclic shifts keeps the array basically at the same position. So the number of DP states is already order nm square. So that's already 200 cubes. That's already 200 cubes. Now let us look at the number of transitions. If you look at the number of transitions, the problem is that when we are doing the number of transitions, we are actually doing minimum. So look at this. When we are doing transitions, we are taking minimum of s dash equal to 0 to m minus 1. So that means our transitions will also take order m time. But the problem is the number of DP states is nm square and the transitions take m time. In that case, the time complexity would be order nm cube. But that would be very huge, right? Because that will be 200 to the 4. 200 to the power 4 would be simply 1.6 E9, right? So that would be much, much greater than 1E8, and this would bound to get TLE. So we need to improve. We need to reduce this number of transitions from big of m to big of 1. So you have to do some optimization. Now realize that this optimization can be easily done because this minimum value, this minimum value dpi minus 1j s dash can actually be computed on the fly while doing the dynamic programming transitions itself. How? Let me show you. So why not maintain one more array mni? Why not just maintain one more array mnij, which is basically the minimum over all s dash from 0 to m minus 1, the value of dp I j s dash. So we maintain this mn array whenever we calculate the dp I j s dash, we take minimum with mn I j on the fly during the dp transition. So in this way, or what we can do, we are also computing mnij along with dpij during the transitions itself. So if we do this, the best part is we do not need to during the transitions we will not loop on this. We can just replace this entire thing. We can just replace this entire thing with mni minus 1j, right? We can just replace this entire thing with mni minus 1j, and the transitions will work. So this will actually help because now the number of transitions will be order one. So this will, so that the actual time complexity and space complexity, so the time complexity of the code will be now the order of n square, and the space complexity of the code will also be order of n square, both of which will pass the time limit. Let me quickly show the code because looking at the program will actually help understanding the solution in this case. So here is the code for the problem. So let us have a look into this. So here I have created three arrays: A, DP, and MN. All of them signify whatever I have explained in the solution. A denotes the grid. DP denotes the 3D DP table where we will store the DPIJS values. And MNIJ is basically the minimum of DPIJS over all values of. So first we have taken the input. I've taken the input, the values of N, M, and K. Then I've taken the grid Aij and initialized the value of MNIJ with infinity. After that, this is the base. Okay, let's discuss the base. So what is the base? Okay. So what is DP00I? So what is DP00I? DP00I signifies what is the cost to reach to 0, comma 0 after such that we make I shift. So in the zeroth row itself. So if we make I shifts in the 0th row, that means first of all we need to add a cost ki because the cost of every shift is k, and we make I shift plus because we have to reach 0, comma 0, and we have made I shift. So that means the value of ai would have come here. So the value of a0i would have come here. And now since we are reaching 0, comma 0 and the sum, a cost of a path is sum of the path, we basically add a0i also to the solution. So this is the simple base case that dp00i is simply a0i plus k times I, and then mn00 is just the minimum of overall the dp00i. So this is the base case. After the base case, here I have written the actual dynamic programming transition. The dynamic programming transition is simple. First of all, because since I've handled the I equal to 0 and j equal to 0 case, I just continue for that. Apart from that, I first initialize dpijs with dpij minus 1s. This is the left part. So this is this part of the transition. Uh, so this is this part of the transition dpijs. For the left part, we have to initialize with dpij minus 1s. This part is common, so we will add it up later. Uh, so you can just look at the code that dpij is simply dpij minus 1s. And then in the num variable, I've stored the value of mn I minus 1j. So basically, I've stored this value mn I minus 1j because I know that this entire thing is simply mn I minus 1j, right? Uh, so that is what I've written. So num is basically mn I minus 1j, and then dpijs is simply nothing but minimum of dpijs and then num plus ks. So ks is the cost we add for shifting the operations, and then we add this common value aij plus s modulo m, which we need to add. So after this value is computed, dpijs, we actually do the optimization. We compute the minimum of mnij and store it with dpijs again in the array. So this actually helps to avoid doing an order n loop, because we actually store the value in some array and the transitions can be implemented in O of one time. So now the answer is finally mn n minus 1 n minus 1, because mn n minus 1 n minus 1 actually stores the cost to reach the path n minus 1 n minus 1 using an arbitrary number of the minimum cost using an arbitrary number of shifts, right? So this is the solution. Uh, so the idea for this problem was pretty clever, but then this was a standard dynamic programming solution, and writing the code was actually pretty simple. Uh, so I hope I'm able to clearly explain the solution. That's it for today. Thank you.